Welcome everyone to the next Bolt-A-Thon. I have Fabrice from ACINQ. He is the CTO of ACINQ, and I'm very pleased to have him here. And he's going to be talking about eclair. So Fabrice, you may take it away.
All right, so good morning, evening, whatever time zone you're in. So I'm going to speak about how we designed and implemented our nodes. And for that, I'll start with what Lightning is about, what our view of Lightning is, and why we made the choices we made. So Lightning, I guess everyone knows a bit what it is. I'm on the page. I've shared my screen. I'm on a Bolt's page. The bolts are the specification for Lightning. It's a kind of RFC-like specification. And when we started implementing Lightning, it was almost like 3 years ago now, 4 years ago. We tried to think first of what the vision of what we wanted to do would be like. There are many ways to implement Lightning. You could write libraries to validate state. You could write. You could base your design on something that can be extended easily. You could base your design on something that can be used in other applications through an API. Our vision for what we wanted to do with Lightning from the start was we want to run nodes. So everything we chose, everything we implemented, and everything was designed was based around the idea that we want to write software that we will use ourselves in production. Something that runs on servers that you start, you don't worry about it, and it's supposed to run on its own and not crash, not fail. It should be easy to debug. So from the start, our view of our work was to implement servers that would basically run with very low maintenance. And for this, we chose Scala and Akka, and I'll explain why. So if you look at Lightning, the protocol, this is like the various bolts. There are two bolts that are really interesting when you want to dive into the protocol. The first one is the messaging bolt. It explains the message format, the wire format that nodes will exchange with other nodes. And the second bolt that is really, really interesting, and it's probably the most interesting if you want to start learning about Lightning, is the actual protocol, because it explains how you establish connections between nodes. This channel establishment is how you open channels. There's a kind of handshake where nodes exchange information. And the really interesting part is this one, how you actually change the state of your channels. So everyone knows that Lightning is about maintaining unpublished transactions. So you open a channel with an unchanged transaction, and then you exchange messages to change how the unpublished transaction that you have is modified when you pay or receive payments. And everything revolves around this. At the heart of Lightning, you have unpublished transactions that we call commitment transactions. And the whole point of Lightning is to set up a protocol to exchange messages to update these transactions in a way that is deterministic and in a way that prevents cheating. So basically this, where my mouse is right now, updates, add HTLC, sign, revoke, is basically the heart of the state machine that powers Lightning. So Lightning is about channels, and channels are state machines. So the question we had to ask ourselves, and it was the same question for everyone, is what tools do you choose to implement state machines that receive and emit messages over TCP? And what we chose, and we don't regret it, was the JVM, Scala, and Akka. So if you switch to our own GitHub repo, you see that basically our work is two parts. We have a Bitcoin library that implements everything you need to deal with transactions and blocks and passing blocks, creating signatures, signing transactions, verifying transactions. And the other project we have is eclair. It's our full node. It's based on this library, and it relies heavily on the actor model. So actors are a way to deal with concurrency that is very different from what you have usually. I'm going to start there. The usual way to deal with concurrency is to use locks. So basically, state is shared among different entities in your code, and you use locks to prevent several parts of your code to modify the same part of your state at the same time to avoid conflicts. It's really cumbersome to use. It leads to all kind of logic errors. It's nearly impossible to debug because debugging means you stop a thread while others are active, and it becomes impossible to reproduce things that happen when all the threads are running free. And it's something that is really hard to deal with. What we chose to implement our channels, which I remind you are state machines, is actors. And actors, the ACA library is a port of what Erlang has been using for years to build telecom software. And the actor model is very different from the traditional share and lock mechanism. It's based on exchanging messages and never ever sharing state. State remains hidden inside actors. So a very basic example here that you have is a calculator. The state here is just an integer, and that calculator receives messages to either set its state, to add something to its state with an add message, subtract something from its state, or just return a state to the sender. And the very interesting part when you look at this on the left is that there are no locks. You don't see any kind of locking, any kind of mechanism to actually handle concurrency. Inside this actor, everything happens in order. You receive a message, you process the message, eventually you could reply something to whoever sent you the message, and there is no concurrency. When it's used, and that's what we have on the right, it's the same rules. You can only interact with actors by sending messages and waiting for answers. This is exactly what you have with channels. So what you have there is a very simple state machine. This one, like I'm going to show you now, channels is a very complex state machine, but it's basically the same idea. You have something that has an internal state that is never shared and that reacts to incoming messages. This is how we implemented the Lightning protocol. So if you look at our code base, you have a wire package that includes codecs for all the messages that you have to deal with the Lightning protocol. Here you can see the open and accept messages that are in the specs. Everything there is codecs for actual Lightning messages that are defined in the bolts. So this is how you add payments. This is how you fulfill payments or fail them. And this is what is sent over the wire to nodes, and this is how you change your state. So basically, if you look at all these messages, these are the events that our state machines react to, and inside everything is ordered, and that is, you don't have to deal with concurrency. They come through TCP connections. They're processed one at a time. You update your state, you reply, and it's a very, very good model because you don't have to think about concurrency ever. For example, here you can see what happens when when you receive an open channel message, you validate its parameters. That's what happens here, and you reply with an accept message. When you receive an accept message, the same, you validate parameters with rules that are also defined in the bolts, and everything is fine. You reply, you switch states, you keep on creating your funding transaction, and when it's ready, you will send parameters to the other side of your channel. This, for example, when you receive a signature in Lightning, I'm going to show you the protocol again to make this really explicit. So this is the most important parts of Lightning if you want to really dive into it. This means A is sending updates to B. It's saying, I want to give you, I want to send you a payment, and A signs its changes. The way it works is A and B have to maintain a view of what the other guy's unpublished transaction looks like. So if you start there, A is adding a payment, is adding a second payment, and then is signing. A is signing all its changes because in Lightning, messages are ordered, and as long as the connection is not interrupted, we assume that messages have been received in order. So if you send 2 updates, what you sign are those 2 updates. Once you receive the revocation and acknowledgements for what you've signed, you assume that the other guy has included these updates in their own view of their commitment transaction. So it's a bit tricky to get right, and it's a bit tricky to have a good mental model for what it does. But basically, the trick to Lightning is to maintain a view of the other guy transaction, and you update this view when you send messages. You sign the changes that you've pushed, and when you receive an acknowledgement, which means the other guy has received all your changes, then you mark them as part of the remote transaction that you're signing. This is something that you can see as you can see there. We've received a signature, so we're going to process it, check that the other guy has the rights to sign. There are actual changes that they've proposed that have not been signed yet. We compute what the transaction looks like. We compute we update our view of their transaction. We update what we think is their view of our transaction. This is what they sign. We check that the signature is valid. And if it's valid, we send our revocation, and we increment our commitment index, which is what happens, sorry, there. Basically, we update our state, we compute a new state, and we send back a revocation. So this is how it's worked for one channel. The really good thing about actors is that most frameworks that are based on actors implement what they call green threads. They're not actual threads, they're very lightweight, and you can have hundreds of thousands of them. The hacker guy said you could even have millions of green threads, millions of actors running concurrently without clogging up your CPU. We run one of the biggest nodes on Lightning on one single machine, and we've had up to a few dozen thousands of actors, and the CPU was like, I don't know, 25% used, not more. So it's a very, very efficient framework because of the way that green threads are implemented and pooled into actual threads.
Hey, Fabrice.
Yes.
So you said you run one of the largest nodes on the Lightning Network, and you handled how many? Like, were those transactions or what? Or channels or?
We have thousands of channels because basically, okay, so maybe not everyone knows this, but we run one of the largest nodes on the network. We also have mobile wallets that is on Android, iOS, maybe next year, but it's hard. But on Android, it's one of the most widely used wallets, and most users connect to our nodes. So these channels, they never show up on Explorers because they're not public.
Yeah.
But if you look at async on 1ML, you see, I don't know, maybe 500, 600 channels, but it's actually much more than this. And we manage thousands of channels on our nodes, on our async node, most of them private.
And what did you mention about it? The CPU use that is still very low, still very
Yes,
manageable.
yes, because as opposed to standard threads, which would kill your CPU if you start having 10,000 of them, actors use green threads. They're like I think Golang has something similar. I can't remember the name, but basically it's some kind of preemptive threading mechanism that makes actors share. You can have lots of actors run on the same actual threads, and it's very efficient. So basically, you can think of it as the state of the actor is saved, and every time it has to be used, and it's processed on a new thread. It's not necessarily always the same one. Messages are processed in order, and when you're inside the actor, everything happens as if it was ordered, but another message might be processed on a different threads. You can't assume that everything is thread local, but it's just a way of dispatching tasks on thread that is efficient, that is not linked to a single thread. And basically, an actor's life cycle is not strongly linked to one particular thread. And messages could be, the next time you process a message, it could be assigned to a different thread out of a different thread pool. I don't know if it's clear enough, but basically
Yeah.
you don't have to match one actor and one thread, and you can have potentially millions of actors with a few hundred threads, and it won't clog up.
Cool. Yeah. And then we have another question from the chat. And the question is, when will Async's node be able to work with Bitcoin Core version 19?
Okay, so I'm gonna go out on a limb and say it should work. If it doesn't, don't blame me. But as far as I know, there are very few changes in. Basically, the issue we have with updating Bitcoin Core is sometimes they change. There are subtle changes in RPC calls, which we use heavily, and sometimes these changes break what we do. It happens between 016 and 017. I think it happened again between 017 and 018. It's not the case here. So let's say I'm 90% certain that your node with eclair should work with 019. This will be confirmed during the next few days, but it should work. As far as I can tell, there are no breaking changes. There are no subtle changes that will impact the way we use RPC calls with Bitcoin Core. So it should work, but it's not officially supported yet.
Got it. Thank you.
So what I was saying is that's the most important parts of a Lightning implementation is the channel, because that's where everything happens. And we believe that using the actor model for channels is a very good fit. And we believe that we've been able to achieve things with Scala and Akka that would not have been possible with other tools, not with the same success and not with the same team. When we started, there were two of us. For a long time, there were just two of us, and three of us after a few months, and we were able to develop what I believe is a fairly good implementation of Lightning, a fairly stable one, a wallet, services like Strike on top of Lightning with just a really tiny team at the time. This is also because of the really good things that the JVM, Scala, and Akka bring. So if I don't know if many of you have used Scala before, but if you have not, even if you are not going to use it for your day job, just have a look at Akka. Use the actor model in Akka. It's a good enough. Akka is so good that it's a good enough reason to give Scala a start. And it's not a silver bullet. It's not something that you can use to implement everything. But if basically what you're trying to do looks like state machines that exchanges messages over TCP, then Akka can do things that are really amazing, because as opposed to many other frameworks, it's invisible. If I go back to this example, you don't see it. A lot of subtle things are happening behind the scenes, like how do you handle threads and concurrency, and what kind of queue you use to queue messages in, what kind of channels do you use to get messages back to the sender, uh, like how it's used there, but you don't see it. And that's really something that is not too common with frameworks. Very often you have to fight them. I don't know if some of you have used Spring, for example, but you have to fight it. It gets all over the place. It gets all over your code. Akka is truly amazing, because that code on the left, you don't see it. All you see is really simple to understand, really simple to use, and extremely simple to reason about, which is the good thing about actors as opposed to threads and locks. And it never gets in the way. And okay, maybe this looks big and a bit overwhelming, but our node is, I think, six or seven times less lines of code. That's what you get with LND or C Lightning. And it's because the tools you get on the JVM, which is not a very popular platform these days, are very powerful and lets you concentrate on what you actually want to do. And all the things that you need, like codecs and TCP handling and connection handling and access and everything, you get them for free. So when I say that we have much less code and C Lightning, Christian usually answers that's the code we wrote, but if you include all the packages we use, it's quite the opposite. And it's true that if you compile eclair the first time we use Maven to manage Java packages, it looks like you're downloading the internet. But these packages are fairly stable. The popular Java libraries have millions of users, so you don't really have to worry about whether they work or not. And you can focus on what I believe is the most important things about code. It's to make code that is easy to read. And easy to read means you can understand what it does, and that's obvious with a lot of languages, but you can also understand what the intent behind the code is, and that's the most important part. If I mean, when we look at our code and when we then switch to the specs, it's very easy to us to see how the specs are mapped to the code, how the subtleties in the specs are implemented. And this is something that you would not get easily with low-level programming languages, because there's a lot of boilerplates and code to deal with. And if you use high-level languages, usually very often it becomes really hard to understand how memory is used, how CPU is used, debugging performance issues or memory issues can be a bit challenging because the choices, the CPU or memory choices are in layers that are so low uh, below what the high level code you're using that you don't see them, you don't even know how to interact with them. The good thing about a lot of Java libraries and especially actors is you get to write high level code, you get to write code that is really easy to map to your specs, and you still can understand pretty precisely how what you implement will translate into memory usage or CPU usage. So as opposed to what some people think, Java is not slow and it doesn't eat memory. It starts with a few, maybe 50 or 100 megs, and then it moves in a linear way. And it can be very efficient from a CPU point of view and from a memory point of view. And it won't be as efficient as C for computations, but this really doesn't matter because uh, the most expensive computations we have to do on Lightning are cryptographic computations. And for this, we can use native libraries that are really fast. But for everything else, being able to just find a clear path between the specs and the implementation really, really helps. And I think that's, it's the choices we made, we don't regret them because it's really hard to find Scala developers, and Scala is not a popular language. But for us, the benefits are are are, are truly amazing. We we don't have stability issues, we don't have memory issues or CPU issues, and with a really tiny team, we can. Our node basically is one of the biggest on the network, and we don't even have to look at it. We check it we check it every day, but it just runs. I think we had one unplanned downtime in 2 years because we tried to optimize something and we were too eager to optimize something that was still working at the time. But otherwise, it's fairly stable. So if you want to have a picture of what the whole thing looks like, it would be, where is it? This. Basically, this is how we designed our node. Again, everything, all these boxes are actors. We get a switchboard because on Lightning connections are multiplexed. You can connect. You can have many channels with the same peer that will be multiplexed over one single TCP connection. So basically, one peer handles many channels, and one switchboard handles many peers. You have a watcher to monitor the blockchain because, as you all know, if the other guys try to cheat, you're supposed to detect it by watching the blockchain. You watch for your funding transactions, and if it's spent, and if it's an old state, then you can compute revocation keys that will let you steal all the funds in that commit transaction. You have a router to compute routes when you want to send a payment to a node on a network, and the rest is linked to the payment lifecycle, how you start a payment, how you check that you've been paid, how you return a pre-image and everything. And this is a low-level stuff related to the transport layer that is encrypted on Lightning. But basically, it's a very simple design that is based on exchanges, messages between actors, and never sharing any kind of state between them, which makes them isolated and which makes them really easy to move to different machines. So, right. So that's also one of the good things about the actual model, and that's what it was designed for in the first place. Basically, actors receive messages modify some internal state, and send back answers to those messages, responses. Whether it's done locally on the same machine or remotely on different machines, it is transparent. So all this could be really easy to split over multiple machines. It would not necessarily make sense to have channels for the same piece dispatched over different machines, but for example, the router, which can do some heavy computations that could be shared between different nodes. This is something you can move to a different machine. The low-level transport layer that does something that is a bit similar to what you do with TLS. Basically, there's a handshake, you compute encryption keys, and traffic is encrypted. This is also something that could be moved to some kind of front that will just handle the handshake and encryption layer, and the rest of the system could work on a different machine. So that's also one of the good properties of using actors. You can move things to different machines very easily if you have to, because you're hitting some kind of CPU barrier usually, or throughput barrier. So that's it for the presentation. Now, if you have questions or things you would like me to dive into a bit more, now is the time.
Yeah, you guys can post it on the chat, and then I can vocalize it to Fabrice for you. So we can wait a couple minutes for people to maybe like think of a question and to like write it down, Fabrice. But yeah, I really did appreciate your perspective and your explanation behind why you guys chose Scala and Akka. I think there's not a lot of, like, I haven't heard much from other implementations about like why they are designing their clients or implementations in one way or another. And it's actually pretty crazy to hear that, you know, CPU usage is like manageable when you guys are managing like thousands of like private channels.
Yeah, I should add that it's mostly because payment throughput or Lightning is not huge yet. So even though we have thousands of channels, there are few days where we have to process more than 1,000 transactions. So Lightning usage is still a bit limited, and this is what would drive CPU usage, because every
Right.
time basically when you pay, you have to sign. When you receive payments, you have to sign, and this is what could become expensive. This would be, I guess, the bottleneck on a single machine if Lightning was to get big, and if you had a node that was hit by lots of traffic. Basically, that's for a single node. So if you have 10,000 nodes doing 100,000 transactions per second, your Lightning is going to do really good. But for one single machine, I guess the bottleneck, and we're far from it, but if we have to deal with a bottleneck, it will be the number of signatures we can do in 1 second, which would be probably in the low hundreds. But
Okay.
we're far from there now. So we don't even process one transaction per second. So we find this is why we don't use that much CPU.
Yeah, I mean, so it would be like, I don't know, 1,000 transactions per 10 seconds or something. I mean, that's still a lot of transactions, I would say.
Yeah, that's the good thing about Lightning. Since it's spread over multiple nodes, the global throughput for Lightning could be huge, even if for each single node it was limited to maybe 1 or 2 per second.
Right.
That's
Okay. So that's really interesting because, yeah, like global throughput does not necessarily equate like real transactional throughput. Like the barriers might be like the routing nodes. Like, let's say the
yes,
topology of the Lightning node is just like there's maybe like a hundred of them, and but then they're like the bottlenecks of how much transactions can actually process in the Lightning network.
yes. But if you have, I think 100 I hope it will be a few thousand routing nodes. If each of them can process, let's say, 100 transactions per second, then your global throughput will be in the dozens of thousands of transactions per second, maybe 100,000. The max, theoretical max would be 100,000 transactions per second, but there will be overlaps between them, so it will be lower, but it's still thousands of transactions per second, because it's not, there's not one single entity everything has to go through, as opposed to, I think that's how Visa work.
So I guess my question is, like, are there plans to try to make transaction throughput on a single machine more efficient, or is the hope just to that there will be just thousands of nodes that will be routing, and so we'll scale that way?
There's something that is already part of the specs. You don't have to sign every time you pay. If I go back to the specs, it was really hard to get a good mental model for this and to implement this the right way. It was a source of bug between all implementations at the beginning, but you can see that here A is sending 2 payments and signing once. So this is, it was, I think, Rusty's idea, and he called it asynchronous protocol. It means you can batch updates and then sign. So even if you can do only 100 signatures per second, you can do more payments because you will batch them. So typically, you would sign like every half second or every second, but you could send many more payments. You would just batch them and sign them once every second. The drawback of doing that is if you have a payment with 5 hops, and if each node is signing only once per second, then your payment will take 5 seconds to go through, which is a bit too long.
Got it. That's really insightful. I actually wasn't aware of that, and yeah, huh. Well, thanks for that, Fabrice. Do we have any other questions from people in the audience, from attendees for Fabrice? Oh, okay, there was one, sorry. I almost missed it. It says this: Lightning is often promoted as more private than on-chain. Do you worry that there is a wrong perception of how much info we leak when we use Lightning, namely IP addresses and on-chain UTXOs with each channel?
It's a very good question. I do believe that that Lightning is more private than Bitcoin, because Bitcoin is not not that private actually. You leak IP addresses, and it's very easy to connect IP addresses and Bitcoin addresses. Lightning has really good privacy because of the onion routing, but as mentioned in the question, you still can spot funding transactions on the network, because when you can spot them when the channel is closed, and that's very important. It's impossible to, or it's all you see when the funding transaction is published is a pay-to-script transaction. You don't see what's inside the script, so you can't tell what it is. But when it's spent, when the channel is closed, you can be pretty sure today when you see a multi-sig 2 of 2 transaction on the blockchain, it's likely to be a closing transaction for a Lightning channel. When you see, and this is in the case of a mutual close, for forced close, which is when there's a problem and you have to publish your current commitment transaction, the structure of these transactions make them easy to spot. So when you go on chain, it's true that you can tell, okay, this is a Lightning channel. What you can't see, however, is the flow of payments. So it's true that opening and closing Lightning channels will leave traces on the blockchain, but payments won't. And that's, again, I think, compared to Bitcoin. It's also very possible to create what I would call virtual Lightning networks inside of Lightning. So when you think of Lightning, everybody think of the public nodes and channels you see on 1ML, but it's very possible to create a network of private channels that are not published. And the activity on this network, as long as it doesn't touches the blockchain, would be really, really hard to analyze and understand. There are also things that are in the works right now that are not ready yet, but we believe that it's possible to delegate root computation to intermediary nodes without losing privacy. It's called Trampoline. You can check it in the specs.
Yeah.
It's not ready yet. It won't be that private at the beginning because there will be very few trampoline nodes, but if it gets adopted, it might be a way to solve, in a way, the routing issue we may have if we have too many nodes. It's going to be a way to speed up payments on tiny devices or mobile nodes, because you won't need to have a full view of the network, and it will still remain private. So that Lightning is not a silver bullet, but I do believe it's much more private than what you have with Bitcoin. And Lightning channels will leave will be spotted on the blockchain, but not payments. And this is what really matters.
Yeah, I think the Lightning Network is great for breaking what I would call like transaction linkability. But even with like closing channels and even well, okay, isn't there technology being developed right now that will obfuscate Lightning 2 multi-sigs? Like I think like Schnorr, or maybe it's Taproot specifically, that will help
Yes.
obfuscate it.
Okay, so the problem you have there is suppose Alice is paying Dave through Bob and Charlie. The payment pre-image will be the same on all the hops. So if it's a bit like the attacks you can have on the Tor network. If the exit nodes colludes with the node you use to reach the network, it can de-obfuscate part of the traffic. And if you see a payment, suppose you run many nodes on a network, if you see a payment that has been relayed by one of the other nodes with the same payment hash, you can be pretty sure that it's the same payment. This is something that could change when we switch from hashes pre-image to
Schnorr.
signatures
Yeah.
once we have Taproot and Schnorr, but it's not soon.
Yeah. Yeah.
Then
It'll be a
it will be
while.
possible to use something that changes at every hop, that you can't really sorry, link between hops, but it won't be ready for some time.
When we do implement something like Schnorr or Taproot, yeah, like are there no longer punishing contracts, or like how does that work?
This is something else. This is L2, L2, which
Yes. Okay,
relies
there you go. Yeah.
on SIGAsh no inputs. So uh, a lot of us, and not just async, think that the penalty ID was maybe not such a good idea,
Mm.
because all the cheating attempts that have been punished were actually mistakes made by people who used old backups or made a mistake and lost funds. I don't think there have been many cheating attempts, but people who messed up with backups and
Yeah.
restored old states and lost money, it happened a lot.
Yeah.
And the other issue with penalty transactions is that you have to remember a lot of states if you want to implement watchtowers. Watchtowers, the idea has been known for as almost it's an old idea. It's as old as Lightning itself. It's 4 years old. No one, as far as I know, is actually running watchtowers, because you need to remember states. Every time your state changes, you need to tell it to the watchtower. So it doesn't make sense from an economic point of view to store an ever-growing amount of data. With L2, the penalty transaction goes away, and basically, if you publish an old state, you'll be able to connect the last state to that old state and resume from there. What it means is there's no longer a concept of punishment. You don't lose everything if you publish an old state, but you don't have to store, if you want to implement watchtowers, you don't have to store all the old revocation data. And you turn a problem that is O(n) into constant storage constraints, and it makes it so much easier that actually I think it's a win. So
Got it. So,
L2 would
so
remove penalty
watchtowers,
transactions.
so watchtowers will still be needed, you think, when we implement L2?
They may be needed, but
They
they
may,
will be much easier to implement, and the cost of running watchtowers will be really easy to control.
got it.
Today, it's like opening your disk, and it's something that will have a cost. And to me, that's the biggest issue with watchtowers right now. That's why we don't see them.
Got it. All right, well, Fabrice, thank you so much for your time. I really appreciate it. I hope everyone enjoyed his talk. And just as a reminder, we're still selling tickets to the next session. The next session is Advanced C Lightning node customization with Rusty Russell. So hopefully I'll see you there. Thanks a lot, Fabrice.
All right. Thank you very much.